அது கூட ஒரு டெஸ்ட் தான்டா.
இல்ல சார் இதே மாதிரி கொஸ்டின் நம்ம
The exam is going on next quarter. Practical. Anti-clockwise movements are what? Negative or positive? Anti-clockwise movements are negative or positive?
Positive.
அப்படின்னா எந்த பக்கம்?
Not.
இங்க உட்கார்ந்து எந்த பக்கம்?
Oh.
Is it towards you or away from? Left hand rotation பண்றேன். Towards you. அப்ப வெளில வரலன்னா எந்த சைடு சுத்தணும்?
Anti-clockwise.
சரி.
Positive.
இது பேர் மாசா. கரெக்ட்.
Correct. Right.
Full tight பண்ணிட்டு. Okay. Even or shared windows closed. Okay. இருக்கு இருக்கிற மாதிரி தான் இருக்கு. Tell me, what problem is that? Well, then not 12th one, what is it? Lamp of a flashlight is okay. So, what is the net potential across? Okay, how to solve it? So there are two batteries, right? There are two batteries, right? And what is the value of each battery? How much is it? 3 cells. How are they connected in series or parallel? So you should think of it. Generally, if you have a torchlight at home, okay, how will you put the batteries? One positive like this, and you will put it in this way, isn't it? Like these two ends will be connected. Like because if you put them in parallel, what will happen? Their potential will be the same. There is no point. Even if you use 100 batteries of same potential, it is not going to be of any use. So this is 3 volt. This is 3 volt. This is how many? So 1.5 volt. 3 batteries of 1.5 volt and internal resistance of 0.25. 1 by 4th. 1/4 of an ohm. Okay. What are we supposed to do? Okay, 3 cells. Potential difference across the lamp. Okay. So battery right connected across a resistor. Is it right? So 3 1.5s connected together will give you 4.5, and 3/4 connected together will give you 3/4 of an ohm, and you have 1.5, which is 3 by 2 of an ohm. Right. So what is going to be the current through this circuit? V is equal to IR. So I is equal to V by R. V is how much? 4.5 divided by R is going to be 3 by 4 plus 3 by 2. How much is it? So 4.5, actually it should be 2, I think. 9 by 4 like 2.25. It will go 2 times. So 2 ampere is the current that is flowing through the circuit. Now they are asking what is the potential across the lamp. So V is equal to E minus I. So they asked only across the lamp. Okay, only across the lamp now V is equal to IR. So 2 into R is 3 by 2. So 3 volt should be the answer. Is there an option? Got stuck. Here, shall I proceed? Okay. Fifth one, what is the question? One point one by 1/3. Unit. 1/3 coulomb per centimeter. Coulomb per meter then. Lambda by 2 pi epsilon naught r. That's it. But you didn't get the answer. E is equal to lambda by 2 pi epsilon naught r. Multiply with 2 and this one with. So 1 by 4 pi epsilon naught into 2 lambda divided by r. 1 by 4 pi epsilon naught is 9 into 10 power 9 into 2 into lambda is 1/3 divided by r is 18 centimeter. 18 into 10 power minus 2. So this will go 2 times. So 2 and 2 will get cancelled. 1/3 into 10 power 11 Newton per coulomb or volt per meter. That is 0.33 into 10 power 11. Is there an option? 33 into 10 power 11. Right? That is for a point charge. Here it is an extended charge. That's what we find using Gauss law, no? Lambda by 2 pi epsilon naught. Right? Any other doubt? Sixth, you have to tell me the question. A parallel plate capacitor of micrometer, micro coulomb. See, microfarad, sorry, microfarad. Charged by a battery of 50. Faster, I need the paper. C is equal to epsilon naught A by D. Because we're talking of 100 microfarad. Okay. Is charged by a battery of 50 volt. The battery remains connected and the plates of the capacitors are separated so that the distance between them becomes double the original distance. The additional energy given to the battery by the capacitor. Initial energy is how much? Half CV square. How much is the value? Half into C is 100 into 10 power minus 6 into V square is 2500. It's called 50. 50 into 25 into 25 is 125. Into 10 power minus 3 is going to be the answer. These many joules is the initial energy. So finally what will happen? Since the distance between them is doubled, capacitance is inversely proportional to distance. So capacitance also becomes half. So half into 50 into 10 power minus 6 into 2500. This goes 25. So 625 into 10 power. But how will you get the resistor value? I mean, 625 into 10 power minus 4. Correct? So 625 into 10 power minus 4 is 62.5 into 10 power minus 3 joule. It is exactly half of this value. So the extra energy that is given is 62.5. 125 by 2. And as far as exam is concerned, don't write anything on the paper. Board exam will have it. Considered as copy. So you can share your question paper. Not write it. So, want, you can always take a rough sheet or they'll give you a booklet. No? I'm not sure if you have started booklet. Although one page only you can make that rough sheet. But ensure that you're attaching the rough sheet also. Don't take anything. Yeah. Anything else? That's it. Shall we get started then? Next chapter. So last class we finished the dual nature, right? Those who are online, are you there? Nithilan?
Yeah, I'm there, sir.
Nithilan, speak, no?
Sir, can you hear me?
Yeah.
Yeah, I'm there, sir.
So, tell me. Right? Just see, whenever they ask, electric current as such does not have direction. Who is responsible for the motion of the charges? You just, that's the answer. That's it. Sometimes the question is too simple and will confuse you. Right. So getting started with chapter 12, atoms. Right. So till now we had been discussing different concepts that were related to optics, right? We discussed optics, under which we discussed about ray optics and wave optics, followed by which we discussed another chapter called dual nature of matter and radiation. Okay, accepted. So the next part, if you see, this atoms also falls under a branch of physics called as modern physics. Okay. So if you observe this atoms, it had been playing an important role not only with respect to this chapter, it had been important right from the beginning of our discussion of 12th standard itself. So when we discussed about electrostatics, right? So what does in electrostatics I talk about an object called as atom, right? So basically, what does an atom consist of? Atom consists of electrons and a central part called as the nucleus, right? And what did we do in the case of electrostatics? We were trying to create charge on a material. We know that every material in this world is made up of atoms, and we try to create charge by either making that atom lose an electron or gain an electron. So by doing this, what we can achieve is the charge. Right? It can either be a positively charged or a negatively charged. So for you to speak about the concept of charge, you need atom. Similarly, you need to talk about the system of charges, you need atom. Similarly, you need to talk about magnetism, you need atom. You need to talk about current and electricity, you need atom. So if you see everywhere, atom plays an important role. That's what we understand from the past. Okay? So in this chapter, you can ask me, what are we going to do in this chapter under the name of atoms? Right? Mainly, we are going to concentrate on the atomic structure. Means we are going to mainly discuss about the different kinds of structures that were proposed and what was the structure which was accepted at the end. So it's a very simple chapter. You already know the basics of the chapter from your 11th standard chemistry. Right? It's very, very simple. We are going to discuss the same thing again, except the fact that we are going to apply a little bit of physics to derive certain formulas. Is it clear? So with this prelude, let's get started. Right. So if you see the different kinds of atoms that were proposed by scientists, so if you date back, right, you will talk about the first kind called as Dalton's atomic theory. So what did Dalton say? So he told that atoms are indivisible. Means atom cannot be further subdivided into any other smaller particle. But later, as the discovery or experimentation process was carried on, we could understand that atom also had other particles inside, subatomic particles like electrons, protons, and neutrons also. So we were going to mainly concentrate on how this evolution has taken place. And with respect to your syllabus, the first model of atom that we are going to discuss is by Thomson. So first is we'll see what is the Thomson's model of an atom. Right. So like how every scientist had the freedom to give their version of how an atom looked, Thomson also proposed something like this. So which we call it as Thomson's model of an atom. In 1898, J.J. Thomson proposed that atom is a sphere. So he told that atom is definitely a sphere, no doubt in that. Right. And the sphere is designed in such a way by nature that this sphere consists of positively charged matter which is embedded in it. What did he say at that point of time? He told that atom as a whole is a sphere with complete positive charges. I'm extremely sorry. I'm sorry. So the first one is Thomson's model of atom. In 1898, what did Thomson propose? So he proposed that an atom is a sphere of positively charged matter. So the sphere as a whole was a positively charged matter in which electrons were placed. Right? The electrons were placed in this manner. That they look like how the seeds in watermelon are present. So that's why sometimes it is also called as the watermelon model, or sometimes they call it as a plum pudding model. Right? Because the shape and the way things are arranged looks in the form. Right? So the arrangement of electrons inside the continuous positive charge is similar to that of the seeds in a watermelon or plums in a pudding. That is why Thomson's atomic model is also known as plum pudding model of an atom. Right? And the important point to be noted here is the question of how the force or how the electrons being placed so close to each other are able to interact, right? So the electrons are arranged in such a manner that their mutual repulsions are balanced by their attraction with the positively charged matter. Because you think of the logic, right? See, even tomorrow, if I have a chance, even I can propose an atom. But I need to give as a theoretical physicist or whatever it's called. So I need to give an explanation stating that, okay, I'll accept that you're saying this is the model of something, there is a structure of something. But how will I accept that it is stable, or how is it going to be neutral? Because in this world, something which is not neutral or something which is not stable are highly reactive. Accept. If I have a charged particle in hand, for example, I have an ion in hand, what will it try to do? If I have a positive ion, it will try to, it will always go in search of a negative ion, and the vice versa happens. So they are most unstable. Similarly, I'll not say unstable, they are most reactive. They'll be ready to bond with their opposite charges. In a similar way, when I talk about the stability, something which is unstable will always try to attain the stability. If it has to attain stability, the only way is by using its energy. Something which is unstable is said to have more amount of energy, right? So what he told us at that point when he proposed, of course, this model is not right, but what explanation he gave is the electrons are arranged in such a manner that their mutual repulsions are balanced. So electrons obviously have mutual repulsions, are balanced by their attractions with a positively charged matter. So he concluded stating that this is the reason why the model of atom that I'm proposing is said to be stable and neutral. Is it clear? here comes an important. So in today's world, we know that there are drawbacks. But what are the drawbacks that are associated? Let's see. Okay. So drawbacks of the Thomson's model of an atom. First thing, so it could not explain the origin of several spectral series in the case of hydrogen and other atoms. Okay. So here when I talk about the spectral series mainly speaks about the different kinds of wavelengths getting emitted when an electron jumps from a higher energy level to a lower energy level. Basically, it is called as emission spectrum also. What is it called as? It's called as emission spectrum because energy is released when electron jumps from a higher state to a lower state. Right? It could not explain the origin of several spectral lines in the case of hydrogen and other atoms. Secondly, so obviously the next scientist who did the experiment to prove that he was wrong, he could have obviously not proved the next part, right? So the scientist who did the experiment subsequent to Thomson was Rutherford. So Rutherford performed alpha ray scattering experiment. So obviously Thomson's model could not give justification to the alpha ray scattering. Right? It failed to explain the large angle scattering of alpha particle in Rutherford's experiment. And third part is it failed to explain the large angle scattering of alpha particles in Rutherford's experiment. Right. So these are the two drawbacks that are associated with Thomson's model of an atom. The next concept that we are going to see is alpha particle scattering experiment. So when I talk about this, basically first I need to know what is an alpha particle. So alpha particle is a helium ion, right? So helium basically has mass number of 4 and atomic number of 2, right? So if you are able to remove 2 electrons, then what charge is it going to attain? It will attain a charge of 2 plus, right? Basically a helium 2 plus nucleus is what is called as alpha particle, right? So that is a helium atom from which both the electrons have been removed. It has a charge of plus 2e and its mass is nearly 4 times the mass of that of proton. So mass of an alpha particle is 4 times the mass of proton. See, again, this concept is also important because if you see the 4th chapter, right, we would have discussed many problems based on an alpha particle and a proton projected into a magnetic field perpendicular. They'll ask you how will the radius change. So at that point, you need to know this concept. So how is the mass of the alpha particle related to proton? It is approximately 4 times. Okay. So how are these generated? So basically, alpha particles can get generated from radioactive elements. So radioactive elements are those elements whose nucleus is unstable. What is nucleus and other things we'll slowly see. So alpha particles are mainly liberated as a product of radioactive source. One of the sources we can think of is bismuth 214, which is collimated into a narrow beam through a narrow slit. Okay. Now, this beam that is getting generated, the beam of alpha rays which are getting generated, is allowed to fall on a thin gold foil. The reason why gold foil was chosen at that point of time is one is maybe I think it was cheap at that point. Secondly, gold is highly malleable and ductile, so it can be drawn into obviously thinner sheets, right? So the beam is allowed to fall on a thin gold foil of thickness 2.1 into 10 power. There is a mistake. It's very thick. 10 power minus 7 meters. Okay. So as of now, you can have it as thin gold foil. I'll check this number and let you know. Okay. So the beam is allowed to fall on a thin gold foil. What happens is the alpha particles get scattered in different directions are observed. Okay. So what happens is alpha particles start getting scattered in different directions, And how are they observed? With the help of a rotatable detector, which consists of what? A zinc sulfide screen and a microscope. Okay. Whenever the alpha particle strikes the screen, it produces a tiny flash. And the tiny flash is also given the name called as scintillation. Are you able to understand what I'm trying to say? So this is how it looks like. So if you look at the diagram, right, you have a lead box, right? The reason why the radioactive source of alpha particle, that is the bismuth, is placed inside the lead is because lead has very less penetration allowance for alpha particles. Means lead does not allow the alpha particles to penetrate through them easily. They can actually block. Okay. So the alpha particles that are getting generated are sent through a device called as collimator. Okay. And you have a gold foil which is placed here. You're able to see? So gold foil. So when the alpha particles are traveling towards the gold foil, you could observe that some of the alpha particles actually pierce through them and some started facing a deviation. Right? And when these deviated particles went and fell on the zinc sulfide screen, with the help of a microscope, what is it you could observe? You could observe some tiny flashes of scintillations getting generated. Okay. So, in this way, the number of alpha particles are scattered at different angles. Okay. And most importantly, the whole apparatus is enclosed in an evacuated chamber to avoid scattering of alpha particles by air molecules. Tomorrow you should not come and tell me that it happened due to air particles because there is nothing except a gold foil and alpha particles present. Okay. Am I clear? So what are the main observations from the alpha particle scattering experiment? So one thing you could say is most of the alpha particles pass straight through the gold foil or suffer only small deflections. Okay. So first thing, that should have not happened, right? Because according to Thomson, the whole atom is positively charged. So helium is also positively charged. So positive charges are approaching towards the positive charge are repelled. But what is observed? They actually penetrated through the gold foil. Similarly, a few alpha particles, about 1 in 8,000, get deflected through 90-degree orbit. Okay. Occasionally, an alpha particle gets rebounded from the gold foil, suffering a deflection of nearly 180 degree. Means it takes a complete turn and rebounds. Right? Right. Okay. So what are the conclusions? As most of the alpha particles pass straight through the foil, so most of the space within the atom must be empty. That is the first point that we can conclude. Second, explain large angle scattering of alpha particles. So what he suggested is only few particles took a turn of 180 degrees or let's say 90 degrees, right? So there is only a specific area where you can logically say that there is a positive charge present because the charges that got deflected were also positive, right? To explain large angle scattering of alpha particles, Rutherford suggested that all the positive charge and mass of the atom is concentrated in a very small region, and that was the first time for which this name called nucleus of the atom was coined. That small region was called as nucleus. Till then, people didn't know that something called as nucleus existed. But here also there is a twist. So according to Rutherford, nucleus consists of only positive charges. But today we know that nucleus consists of positive and neutrons. That is protons and neutrons. But at that point, when this proposal was made, nucleus had only positive charge. Okay. And the nucleus is surrounded by a cloud of electrons in such a way that the total negative charge produced due to the electron is equal to the total positive charge on the nucleus, so that the atom as a whole can be concluded as electrically neutral. So that you can conclude that the atom as a whole is electrically neutral. Am I clear? Shall I proceed? So the scattering of alpha particles, why did this happen? It was due to the Coulombic repulsion that took place between the positively charged alpha particles and nuclei. Here we are calling it as nuclei because there are many atoms present and many atoms have many nucleus, right? Which is in plural called as nuclei. Clear? Shall I proceed?
Yes, sir.
If you see, if this spherical part is the atom, then this central part is given a name called as nucleus. Most of the alpha particles got penetrated through the gold foil, and after some time, yes, they got deflected. That's a different story. But if you see, there are certain alpha rays which went almost close to the positive charge, and they took a turn of 180 degrees, right? Where they could not touch the nucleus, obviously, right? So they could reach a maximum distance, right? A possible maximum distance possible till the nucleus. So if you try to measure the distance between the nucleus and this point T, where it took the 180-degree turn, then you call that as R naught. Where this R naught is called as the distance of closest approach. It's called as distance of closest approach. So an alpha particle like 1, an alpha particle like 1 and 1 dash passing through the atom at large distance from the nucleus experience small repulsion and passes almost undeflected. Okay, they pass almost undeflected, right? But the alpha particles like 2 and 2 dash, so 2 and 2 dash, what you can observe is which pass closer to the nucleus experience large repulsive forces and hence scatter through large angles. Very rarely an alpha particle like 4 travels head on towards the nucleus. The strong repulsive force slows down the alpha particle, which is finally stopped and then repelled back along its original path. So whatever story I discussed, right? And that distance is what we call it as the distance of closest approach. So what is the definition of distance of closest approach? As an alpha particle directly approaches the center of the positive nucleus, it must experience coulombic repulsion and hence its kinetic energy gets progressively converted into electrostatic potential energy. That is what we call it as electrical energy. So I repeat, the kinetic energy which the particle had is completely converted into electrical energy. So what happens due to this? At a certain distance r naught from the nucleus, the alpha particle stops for a moment and then begins to retrace its path. Where you can say that the scattering has taken place through an angle of 180 degrees. Right? Hence, this distance r naught is called as the distance of closest approach. At this distance r naught, the entire initial kinetic energy of the alpha particle gets converted into the electrostatic potential energy. So, mathematically, I can say half mv square is converted to 1 by 4 by epsilon naught into alpha particle charges 2e and the nucleus charges Ze, the whole divided by R naught. So this is the formula for electrostatic potential energy. So from this, if you rearrange the equation, R naught will be equal to, so 2 will cancel for 2 times. So 2 and this 2 will cancel 2 times. Right. So R naught will be equal to 1 by me square into pi epsilon naught multiplied with Z e square. Should I proceed? So the next point that we'll be discussing is called as impact parameter. Okay. So how is it defined as? See, it is defined as the perpendicular distance of the velocity vector of the alpha particle from the center of the nucleus when it is far away from the atom. So this is V. Okay, this is called as the impact parameter. This is called as the impact parameter. Clear? So generally for large impact parameters, the repulsive force experienced by the alpha particle is weak because of the inverse square law character, and the alpha particle passes undeflected. Means if it is far away, if the impact parameter is more, it means that it is far away from the line of action with respect to the nucleus. Hence what will happen? Repulsive force will be less. So for small impact parameters, the repulsive force is large, and so the alpha particle is scattered through large angle. So having all these things in mind, we can define the concept of impact parameters, mathematical formulas. B is the symbol used for impact parameter. So B is equal to 1 divided by 4 pi epsilon naught into Z E square mod theta by 2, the whole divided by K, where theta is called as the scattering angle. Where theta is called as the scattering angle, K is called as the kinetic energy, and Z is called as the atomic number of the nucleus. Is it clear? So we have seen how the Rutherford's model of experiment was performed. Then the concept of distance of closest approach, then impact parameter. Right. The last point you can make a note of this. For head-on collision, when the alpha particle just aims at the center of the nucleus, the impact parameter is 0. The alpha particle is reversed back along its original path. So as we discussed, if the impact parameter is 0, it's less, more is the repulsion. So when it is 0, we have the maximum repulsion. Okay. Now, this is all about Rutherford's model of atom, but we are supposed to see the drawbacks. Okay. So, according to Rutherford's model of atom, an atom consists of small and massive central core in which the entire positive charge and almost the whole mass of the atom is concentrated. And the core is called as nucleus. Right? The size of the nucleus is approximately 10 power minus 15 meter, which is very small as compared to the size of the atom itself, which is almost 10 power minus 10 meter. Okay. Next is, the nucleus is said to be surrounded by suitable number of electrons so that the total negative charge is equal to the total positive charge of the nucleus. An atom as a whole is electrically neutral. Okay. And an important point here is the electrons revolve around the nucleus in various orbits just as planets revolve around the sun. The centripetal force required for the revolution is provided by the electrostatic attraction existing between the electrons and the nucleus. So this is an important point to be remembered because this is the point on which the contradiction by next time is started. Right? Okay. Last concept for the day is the next topic, that is limitations of Rutherford's model of an atom. So firstly, according to electromagnetic theory, if you have an accelerated charged particle, it must radiate electromagnetic energy. So I repeat, according to electromagnetic theory, if you have an accelerated charged particle, it must radiate electromagnetic energy, because if you revisit the concept of EM waves, we can say that the source of electromagnetic wave is whom? Accelerated or an oscillating charged particle, right? An accelerated charged particle must radiate electromagnetic energy. Secondly, an electron revolving around the nucleus is under continuous acceleration from the center because it is experiencing force, right? So according to electromagnetic theory, what should have happened? This electron, which was continuously accelerating, should have lost energy and move in orbits of gradually decreasing radius. Means it should have started moving like this, and at one point of time the electron should follow a spiral path and it should finally collapse into the nucleus itself. So if this kind of a scenario had happened, then of course this theory does not support the concept of stability of matter. Because when the electron collapses into the nucleus, then there is no stability or atom you are going to talk about. It is all about nucleus. Right. Next is, as the electrons spiral inwards, their angular velocities and frequencies would change continuously, and so the frequency of emitted light will also change. As electrons spiral inward, their angular velocities and frequencies will also change continuously. So the frequency of emitted light will also change, and this process should emit a continuous spectrum instead of actually observed line spectrum. So what happens is you can actually observe a line spectrum, but at this theory work, it should have emitted continuous spectrum. So this is all about the two models of atom, and the last concept that is there is Bohr's model of atom, which we will see tomorrow. So with that, this chapter is done. Okay. Screen recording of class. Mithran, we can leave.
Yeah, thank you, sir.